Yeah, this is like you guys are the bold, beautiful, and the brave, I think, coming up 8 a.m. in the morning, right? So that's goodness. Yeah, you can go ahead. Why don't we get started? I'm Ripin Checker. I lead the OCP Telco Edge community along with Lauren and John will be on stage as well. So it's a packed agenda. So thank you for joining. You already heard a lot about AI everywhere, edges everywhere, and when you look at all the server shipments, a lot of the server shipments are moving towards the edge in terms of percentage, right? So if you look at the total shipments, edge is becoming very important. It's like a $50 billion market. Edge shipments for servers are going up to 30% or so. So it's really an important thing. So with that, we have a lot of content for you covering all the specifications that are coming to the community. And with that, the first presenter, we have Kylie and Keyur. They're going to walk us through open aggregation router. Just because so much traffic is coming with edge computing, there's a huge place with open aggregation routers. And also there's a space for the network operating system. So you're going to hear from Kay and Keyur.
Thank you. Good morning. Good morning, all. And thanks for coming so early at 8. My name is Kylie. I'm with Ufispace here in San Jose. My partner from Arrcus, I'll let you introduce yourself.
Good morning, folks. My name is Keyur Patel. I'm from Arrcus.
Great, thank you. All right, so we're going to spend the next 15, 20 minutes to talk about the aggregation designs, particularly for the data center. And we must say that today when we design a data center, it's quite different than how we used to do it 3 to 5 years ago because of all these new requirements. We talk about the challenge and the new demand and all that. And then, of course, with our partner, we talk about the benefit, the joint solution from our hardware and the software perspective and the go-to-market strategy. So we kind of color code the demand and also the challenge. And I want to point out a few key things of how we design a data center today and even how it's so different just like 3 years ago. With a lot of demand on the AI that needs to be built into the intelligence of the data center, some of the big data, Hadoop, and all these other things. And some of these turns into the capability of the network switches to be able to program, so the programmability become even more important than before, and not to mention the orchestration, the provisioning, and all these other things. In the old days meaning like 3 years ago, we focused still a lot about DCI, data center interconnect, redundancy, and all these other things, but now has a lot of software intelligence built in because the catch-up of the AI, you need to have a lot of those kind of things built into the solution. So in the next 10 minutes, we're going to talk a little bit about that. Our company mainly focuses on hardware, firmware design, and then Arrcus has all the intelligence that port into the control plane that make this whole solution. And with that, I'm going to talk a little bit about the merchant silicon positioning. If I can call your attention to the diagram on your right, this is kind of like how we do that balance between the throughput versus the feature. You see the throughput on the vertical and then the feature on the horizontal. So we actually kind of borrowed this diagram from our friends in Broadcom. Vertically, we have the traditional Tomahawk. And then on the bottom, we have the DNX, like the Jericho and all that. And then somewhere in between, we have the Trident. So the Tomahawk, which really only focuses on the speed and feed and throughput is all it cares. And then kind of with a little bit of balance, the Trident is a little bit less on the speed, but start giving you some programmability and feature. And then what we focus today is the one all the way on the right-hand side where we circle it, and that is the DNX. The DNX made up with all the Jericho. If you talk to some of the Broadcom folks today, the Jericho 3 has been announced and some of the 5 nanometer chip and all that. Now, why are we picking this one for data center, which traditionally was built for telco? And it's all application driven. And one of the things we're going to talk about really quick is the deep buffering. And we're going to show you a table, I believe, actually it's right here. So if you look at, if I call you to the second bullet item, just to kind of give you an idea, if you look at the DNX chips on IPv4, you can cache up to 20 million entry, versus if you take a look at the XGS, you're looking at about 10%, about 2 million on IPv4. And when you go to IPv6 with 32-bit address, that number even become very challenging. So that's the reason we picked another solution. We have been having solution using XGS for the data center, but we are evolving into the carrier chipset into the data center. All right, so really quick, just kind of talk about the boxes that we bring to the table today. When you design aggregation either for carrier or aggregation for data center, that is very important to have one design concept in mind, and that is to balance between the high density of the port requirement as to compare to the cost of the total solution. Because by definition, aggregation, you need high density port at a relatively low cost solution because you're aggregating a lot of devices into a central location before you hit the core. So balancing between the cost and the port density is very important. So with the concept in mind, we have picked the Kuhlmann 2C chipset to build our solution. And within our family, we picked 3 boxes to share with the audience today. The Kuhlmann 2C, just a little bit on the spec, is a 16 nanometer chip, and Broadcom, I think it came out around 2018 or somewhere around that. So it's not, compared to the Jericho 3, which is a 5 nanometer, this is not the latest and greatest. But again, we picked the Q2C to balance the performance and also the cost, because we have to build up aggregation device that fit the market's demand. A 16 nanometer chip, and this one is switching at 2.4 terabit per second. That's the backplane. It's a Kuhlmann chipset, so it doesn't have the switching, cell switching part like a Jericho. So we focus the entire 2.4 terabit for port density, and we tend to design something called the non-blocking, meaning all the port will within the 2.4 terabit, all right? So really quick before I turn over to our friends at Arrcus, we are presenting 3 boxes today, and basically if you look at from your left to the right, we have the dual Q2C, dual Q2C design that focus on what we call the high density of 100 gig port. And then the middle one, the 32, that one is for the regular density. So we went from 6400 gig port for aggregation down to the 32 in the middle. And on your right-hand side, that's probably the most exciting thing, because a lot of the time you see aggregation is in a spine and leaf, a 2-tier for horizontal scalability. So the last one is really for the leaf with the high density for the 25 gig and 10 gig, because a lot of the server connection or the access connection are still into that port density. One last thing I want to mention to you, on the box on the right-hand side, you notice that box we actually support TCAM. Because when you have thousands and tens of thousands of access control lists, you want to safeguard the access control list with an intelligent TCAM table done in hardware right at the edge before doing it at the leaf before you go up to the spine. So when you look at the 3 box, that's why we highlight the one on your right-hand side. The 25 gig has a TCAM option for the reason. It's all kind of like, reverse engineering to fit the design. As traffic comes in, you want to have all your access control lists right at the edge before it propagates to the rest of the network. All right, so that's kind of like a 5 minutes on the hardware. I'm going to turn over to my partner to talk a little bit about the software.
Thank you. Thank you. So here, Kai and team has built a wonderful set of boxes that are out of Qumran or DNX chipset. Let's talk about software that complements this hardware. What essentially is a NOS? If you ask a question, you can take a step back and sort of slice it down into 4 major software components. First one is the SDK that runs on the chip. And that actually drives the chip, that programs the chip. The second piece of software is a set of drivers that we would typically get to drive the components that are on the box, like fan, temperature control, so forth and so on. The third piece of software would be the base operating systems, what we call as Linux, or you name an OS of your choice. That would be used, that does process memory management, and the fourth piece would be control plane that runs on the box. When you fuse all 4 of these pieces together and run that on the hardware that Kai and team were talking about, it becomes magically a router or a switch, depending on the chipset you're talking about. A little bit about this software, it's a 64-bit, which means from a router-grade platform standpoint, it can scale to millions and millions of routes. Since the white box itself support 8 cores and 16 cores. This is designed to be multi-threaded, fully distributed operating system that can actually exploit core counts, not just at the process level, but at the workload level within the processes as you break it down, right? It's probably one of the best in that category that can actually leverage multi-core aspect very nicely. Northbound is fully programmatic, as you can see, whether you come from RESTconf or NetConf, it is native open config. It supports full-scale telemetry, not just at the chip level, forwarding level, but at the control plane level itself. And last but not the least, it's quite open in sense that it is fully standards-based. From a fabric standpoint, it supports MPLS and IP both. Advanced form of MPLS as well with segment routing, as well as SRv6. So when you build a box that has a software that allows a chip to unleash the potential alongside with the box, there are a few interesting use cases that we can go after. The first one is telco edge data centers. Edge compute is growing, and as a result of that, not only would you need points at the packet gateways that are sitting right behind BBU towers, but also your CRAN network as well as your transport network that resides in there. And there, from a feature standpoint, it supports segment routing, like I said, full MPLS stack. All routing protocols are supported, as well as from fabric standpoint, EVPNs with layer 2, layer 3 services are also supported. Note that as Kai mentioned, the chip itself supports low latency cut-through switching as well as routing. Therefore, at a chip level, you can do, as Kai was talking about, whether you deploy Q2C, Jericho 2s, or so forth and so on. It can do 2.5 gigs to 10 gigs and above non-blocking traffic. So it makes a fairly impressive router or a switch, if you will, when you start looking into it. So that's the first use case that becomes very, very interesting in the 5G arena. The second one, as Kai mentioned, a couple of years back when we looked at data centers, that was predominantly compute. Now the data centers are increasingly also transitioning things like Hadoop clusters, so your storage, to Ethernet. At the same time, AI is just coming up on the horizon where data centers are being wired to do AI networking. That is predominantly also that there's going to be a big factor of Ethernet. When you start to look at that, deep packet buffer switches become very interesting, because you can buffer the packets, so minimize the loss. Second, you can tune the packets rate, and therefore you can minimize the jitter that you are looking to get out of the network. So this becomes very, very interesting, and more importantly, because of the high radix, it can scale horizontally very nicely. So that's a second use case where you can deploy this extensively. The third use case that becomes very interesting is, as Kai was talking about earlier, AI-driven data centers. Now, when you look at AI, there is a big hype about AI, which is truly the right one, and folks are riding the wave. But when you start to look at network that AI would want, the kind of network that it would require is, you need to have a lossless connectivity. All these algorithms, LLM and LLMs, aren't defined to tune very well with the loss like TCP is. So as much lossless as you want, and there the buffering will count, as Kai was mentioning earlier, from the hardware perspective. From a software perspective, just don't crash and stay up as much as you can. From latency perspective, not only do you need a low latency, but you need predictable latency. One great way of doing that is reduce the depth in the class network that you are building. But that comes only when you have a higher radix where you can spread out and have higher number of ports. Therefore, you don't have to increase the depth. So the boxes that are out here with the merchant silicon support that we are talking about allows you to do that. When you sort of get to a lossless, low latency, predictable latency, and low jitter, fabric side visibility becomes very important if you want to do some kind of tuning on the traffic engineering or so forth and so on. So that becomes very interesting in that particular aspect, which the software and the combination of hardware through the chipsets already supports it. High availability is going to be very important. As I said, don't crash the network. Don't try to break the network, and keep the network as much up as possible. This is combination of both hardware plus software. So when you fuse this hardware with the software that we've been talking about, it builds a box that is very much applicable to the likes of the Gen AI data centers. Yeah. And finally, to summarize, as I was talking about, the benefits are huge. You can start deploying it. I mean, this is naturally available for data centers that are doing compute today, but it becomes super interesting when you start to look at the next-gen data centers that are edge compute as well as Gen AI-based, and of course, storage that is migrating towards Ethernet. It can address multiple use cases. One big thing to always watch out for when you use a software hardware combination of a box like this is, hey, how can I manage it? Because a cost to manage a network cannot be ignored. And here, for the fact that the combination of hardware and software provides you with fully programmatic environment that you can automate it from any point, local or in cloud, makes it super attractive. So all in all, it builds a great product. For you, Kai?
Sure. Oh, yeah, I got my mic here. Okay, so call to action. This has been submitted to OCP library, has been uploaded around Q3 this year. So if anybody interested in more detail, it's up in the library, it's open, and we share this whole architecture with our OCP part of the submission. So a couple key takeaway about this newer design as compared to before. As I mentioned, even as recent as 3 years ago, when we design a data center, what are we looking at? Throughput, the density, DCI data center interconnect, contingency recovery, global load sharing. All these things are still important, but more importantly is the lossless that Keyur talked about because of the higher demand, the newer demand of the some of the emerging application I would call, like the AI, the Hadoop he talked about with the big data on the storage side and all that. So that's why we have all these newer requirements into the data center design that we brought to you this morning. Hope it's worth to the information to share with you in the last 15 minutes. So with that, I'll turn this back over to you, or we can close.
Okay, any questions? Great session. Any questions from anybody? All right, please.
Yeah, on my left here. Yes, please.
Thank you. Wonderful. Can you make any comments about security? Do you do things like MACsec, IPsec? And if so, I noticed you had a line which said IEEE 1588 v2. How does security and that kind of interplay?
Yeah, so a lot of these boxes, we have to support 1588 version 2, and for those people who are interested, it's called the Precision Timing Protocol, PTP. It's more the legacy coming from the carrier side, because carrier really care about PTP. Q2C itself, first of all, I want to answer the IPsec and then the MACsec. Some of the chip natively will support MACsec. Q2C is not one of them. There's Q2C plus the newer generation will. So we are highly depending on the IPsec. IPsec has kind of the component based on the network operating system. And also in a certain design, we also can do some hardware acceleration with the key exchange and all that. So that's kind of a 1 minute answer.
And I would add on top of that, as while you were alluding to forwarding side of the security, and the question was pretty much focused on that, but if you start to look into 5G deployments, the control plane side of the security also becomes very interesting. So not only can you exploit the forwarding level security that Kai talked about, but there is additional security in software, and this is partly due to the fact that software is designed from the first principles and we haven't inherited anything else. So it allows you to build inherently very secure software. Case in point, you can do BGP-sec. You have all the incoming connections protected using SSH. You have very solid COP and ACL, extensive feature list support that makes it inherently very attractive for service provider deployments, yeah?
Great, thank you. I think we had 1 minute more.
Yeah, we've got one more question. Anybody? All right.
For your mobile backhaul use case, I try to figure out where are you going to deploy your open aggregation box from that pictures. I could not figure out. So I remember in that picture, you have like the left side with E node B, G node B, and the right hand side you have, yeah, that's the one. I try to figure out what is the mobile backhaul here.
Well, so couple of use cases can come out of this. First of all, the cell site router becomes very interesting, as Kai mentioned, because you can do the timing protocols as well as layer 2 basic, as well as layer 3. Cell site becomes very attractive. Now, one other interesting use case that we have also developed alongside, which actually allows you to terminate GTP right at the edge of the 5G networks, wherein right behind the BBU towers, where you get the GTP packets, and then do IP from that point onwards using a brand new fabric-based technology that both the companies have come up with, which is SRv6 based mobile user plane. And if you look at that, then you practically take that and deploy everywhere from right behind BBU, which does the UPF offloaders, if you will, to the core and the edge and the aggregation, as well as up to the edge compute stack.
Okay, are you going to deploy a pair of your open box? One is on
Can we do this? They are going to be here. If you don't mind, I would like to get the second presenter up. So thank you to
Thank
Kay
you.
and Keyur.
Thank you.
For your session.
Thank you.
All right. John, are you ready to get going?